What we're going to do here is look at a couple of examples of Laplace transforms here in Chapter 2. The first example is an exponential times a sine, and we want to find the Laplace transform of that. The basic ideas here are for us to remember that the sine bt, its Laplace transform, is b divided by s squared plus b squared. Second thing to remember, to have at the tip of our tongues here, is that when we multiply an exponential times any function of time, its Laplace transform is that of f with the Laplace variable s shifted by a. So these are things to memorize, if you will, to remember. They're covered there in pages 2 and 4. So what this says is that with these two ideas we can derive the important result, which is easier, I think, than trying to remember its form, is that the Laplace transform of EAT sine BT is equal to the Laplace transform of sine with s variable shifted by a. So this is s minus a squared plus b squared. Therefore, this example for the y of t that we have, y of s then, is the Laplace transform of e to the minus 5t sine 7t is equal to b, which is a 7 divided by s minus a minus 5, so that's a plus 7 squared, or 49. Let's check that. Let's check our algebra here, making sure that what we have abides by the initial value and final value that we know. So again, this is an important thing to remember. It's a result there on page 2 of the notes. So we'll check the initial value for y. We know what it is. Let's make sure that our Laplace transform gives us that. So the initial value theorem says we multiply s with y of s. We take the limit as s goes to infinity. So that's going to be the limit then of 7s divided by s plus 5 squared plus 49. And one thing I find easiest to do when I'm taking a limit like this is to get everything in terms of fractions of s. So what I'm going to do is factor out an s from the numerator, factor out an s squared from the denominator. That gives me a 1 plus 5 over s quantity squared plus 49 over s squared. And the reason for writing it in this form is that I know as s becomes large, then things like 5 over s goes to 0, 49 over s squared is a 0. So we end up with a 7 over 1 here. This here becomes a 1 over s, which that fraction goes to a 0. So it's a 0 times that, so it's a 0. It checks out. We know that the exponential times the sine truly is a 0. We didn't prove anything profound here, but we just made sure that our result makes sense. On the other end, if we take s times y of s and we let s go to a 0, we get the final value, the time equal to infinity result. So I take the limit here of s going to a 0 of 7s divided by s plus 5 squared plus 49. These limits are usually a little bit easier to see because the numerator goes to a 0, the bottom goes to a 25 plus 49. So this goes to a 0 over whatever that ends up being, 74. So that's a 0, and that checks out. So it's always good to use these to check your results to make sure that your algebra makes sense. In both cases here, we know the exponential starts out at a 0, and we know because of the decaying nature of the exponential, it ends up as a 0. So this example here was using the fundamental ideas right here. Remember those. And then this equation, you don't have to remember its form. It naturally comes from that.